Welcome to Lesson 7, Introduction to Vertical Projectile Motion. So we've moved a little bit from talking about momentum and energy, but we're still going to talk about energy a bit later on when we talk about work. But now let us now talk about vertical projectile motion. So at least by the end of this lesson, you should be able to explain what is meant by a projectile and use equations of motion to determine first the position, the velocity, and the displacement of a projectile at any given moment. So that is our goal with this. Remember, these videos are not enough. So you also have to, after we do a problem here, you also have to go back and to try to do similar problems on your own and see how is it that are you able to understand them? Are you able to tackle them? If you're struggling, you can always send a message to me personally or in the WhatsApp group. So yeah, let us just get straight into it. So what is a projectile? The standard definition is that a projectile is an object that is launched. So for example, if you throw this object up, you launching it, and when it moves only under the influence of gravity, we call it a projectile when it's like mid-air or in the air. And then the most important thing, we're going to talk about a few things to note, especially in terms of projectiles that will help you very much when you're doing calculations. And the first thing is that projectile moving upwards or downwards. So let's say you have a ball and you launch it, you throw it in the air, right? And then it's moving upwards, so its initial velocity would be up. But then this, because it's moving under the influence of only gravity, it means that it's accelerating at with gravitational acceleration g. So that gravitational acceleration is always downwards. Even when this ball moves down, so now it's moving down, so this is maybe the final velocity, it went up, it went down, it will still, the gravitational acceleration will still be moving downwards. So projectiles moving upward or downward always accelerate at a constant acceleration of g, and we know g to be 9.8 meters per second squared. So yeah, so whether the object is moving up or down, acceleration is always downwards. So that is one of the important things to know. And then another thing would be that projectiles that have an initial velocity that is going upwards, so if there's an initial velocity and it's going upward, will have a zero velocity at maximum height. So for example, let's say you throw this object, this ball from here. Let's say you start here, maybe this is at 1 meter, and then it stops there at 2 meters. So that is the maximum height that it reaches. So let's say you throw it at a velocity of 2 meters per second. This velocity will decrease up until here at the maximum height. Let's say Vmax or Vm is 0 meters per second. So if it has an initial velocity upwards, at maximum height, this is something important to know. At maximum height, it will have a velocity of 0 meters per second. So that is also the second thing to take note of. So let us now imagine that you have a ball and you launch it from a certain height. So remember, because it's in the y, let's call that initial height, and we say it's yi. So this is where you launch it from. And maybe let's draw an axis. So we have maybe here time in seconds, and then position. On this side we'll have position. Let's say it's in meters. And then, okay, so it's in meters. So you launch your projectile from this point. Let's say this is 0. Doesn't always have to be 0. And we call this yi. So yi is 0 meters. And then after 5 seconds, so here is 0.5, meters, and then 1 meters. So after 5 seconds, your projectile now has hit a position of about what is it, 0.5 meters, and then maybe after an additional 5 seconds it will have reached the maximum height there at 1 meters. And then remember we said there the maximum height vm, the thingy, the velocity would be 0 meters per second. We don't know what the initial velocity is there, and then reaches that height, and then it will start now coming downward. So after maybe another 5 seconds, 15, it's at the same position, it's at 0.5 meters, and then finally it returns to the position. So this would be at 20 to finally return to this position where it was launched. So this would be YF, which is also at 0 meters. So a few things to note. This graph is going to form some sort of a parabola. So it is actually called a position versus time graph, and it is a parabola. But in the next lesson we're going to talk about all of these graphs. And what are you noticing? So your finger was launched here, your projectile was launched here at 0 meters, and then its final position is also at 0 meters. So that means the change in displacement, the change in y, would be yf minus yi. So that's 0 minus 0. So the change in y is actually just 0 meters. There is no displacement. And another thing, the time it takes for the projectile to move from the initial position to the maximum height is the same time. So it took about 10 seconds. And it's the same time that this projectile moves from its maximum height to return to the same position. So the same position of 0 meters. So we have something that is called the time symmetry. Time symmetry. And it is exactly what I have just described. Okay, so now we've written it down, the time symmetry. So the time it takes for the object, so remember, for the object to fall back down from maximum height. So from maximum height to fall back down to the point at where it was launched is the same time that is taken for the object to reach the maximum height. It is the same time that this object has taken from here to here. So this, remember, will just be maximum height. Let's call it H max. So the time from here to here is the time from here to here. So that is something that you need to know. The next thing that is important to know is the magnitude of the velocity. So in terms of velocity, the magnitude of velocity at the same point on the upward or downward motion will be the same. The only difference will that the direction will be reversed. So we said here maybe this projectile was launched at an initial velocity. Let's say it was launched at 2 meters per second. And then when it reaches here, remember its velocity is decreasing, it's going up. So maybe here V is about 1 meters per second. And then here finally it's at 0, it stops, and then it falls back down. The now it's falling down, so the velocity is down. So the velocity here would be the same velocity, the magnitude of the velocity here will be the same as this one. So it's going to be 1 meters per second, but the direction will be reversed. And to show that, we put negative, so it's going to be negative. Here, the final velocity here would have VF. It will be the same as the initial one, which is 2. Okay, I need to create space now. So here at this point, so we would have VF, which is 2 meters per second. But then because it's this, the motion of this is actually pointing down, it's going to be negative. So that is also an important thing to understand. knowing these things will help you very much in terms of solving these problems related to projectile motion. And next up, we're going to talk about equations of motion. So these are your equations of motion for projectile motion. I think you introduced to this equations in grade 10. The only difference now is that we are considering vertical motion, so that is up and down. Hence here, instead of a change in x, we have a change in y, and here instead of a, which was our acceleration, we have g, which is our gravitational acceleration, because our projectile is accelerating at that acceleration. So as we know, Vf is the final velocity of your projectile, the initial velocity. G is the gravitational acceleration. This is the change in time. Delta t is actually just your time interval measured in seconds. What else? I think I've defined everything. Yes. Oh, and then the change in y would be the change in position. So now, if you look at all of these equations, you notice that here there's no change in y. At this equation here, there is, what is missing here? There's no g, or gravitational acceleration. And here, we don't have no final velocity. And then here we don't have, what is it that we don't have here? We don't have change in t. No change in t. So for each of this equation, there's one variable that is missing. So when you solve those problems, maybe let's say you given Vf and Vi, but you're not given a change in position. So you should know that you are going to use this equation. Maybe you are asked to find the time. But now let us just put this into perspective by actually doing a calculation. Okay, so we have a question here, and it said Zingy throws a tennis ball straight up into the air, and then it reaches a height of about 80 centimeters. So that is its maximum height. And then question A says that we should determine the initial velocity of the tennis ball. And then the second question is, how long does it take the ball to reach its maximum height? So now to solve these problems, we have to go back and look at our equations of motion and see which equation of motion we're actually going to use. So, okay, this is just a schematic representation of the situation that they described to us. So they said that the tennis ball was thrown at an initial velocity. They didn't tell us the magnitude of that initial velocity. And then it reached the maximum height of 80 centimeters. So the important thing here is that you need to convert this 80 centimeters, because this is not in SI unit. So you convert it to meters, because position is measured in meters. So to convert from centimeters to meters, you simply divide by 100. So 80 divided by 100 is going to give us 0.8 meters. So that's the value you're going to use in the calculation. And then and when it reached the maximum height, this tennis ball, it had a velocity of 0 meters per second. So we can say, okay, let's call this position A, or initial position. So position A and position B. And then write down what the information that we know. Do we know what VI is? No, we don't know. That's what we're looking for. Do we know what VF is? Yes, because here, from here to here, this 0 meters per second is actually the final the final velocity. And then what else do we know? We know the change in y because we have this height. So the change in y is given by 0.8 meters, and it's positive because it's moving upward. And then do we know the change in time? Nope, we don't know it. So now we have to actually look for an equation that doesn't require us to provide the change in time, but then it has VI, VF, and a change in Y. Okay, so this equation one requires us to provide the time, so we don't use it, even this one. But if you look at this equation, you find that it doesn't require us to provide the change in time or the time interval. And then we have Vf, because we said it's 0 meters per second. We have this is what we're looking for. So this is the equation that we actually going to use. Okay, so let us use it. So we're saying that Vf squared equals to Vi squared plus 2g change in t. And I forgot to include that g is 9.8 meters per second. And then in terms of direction, if we say up is positive and down is negative, this means that g, because it's always acting down, is going to be negative 9.8. So please be aware, if we had selected downward motion to be positive, g was going to be a positive 9.8. So that is something to take note of. Okay, so now we just have to substitute, right? So now we have Vf squared is going to be 0 squared equals to Vi squared. We don't know, that's what we're looking for. To negative 9.8, a change, like that's a change in y. A change in y, which is 0.8. All right, and then you can just put this whole thing in your calculator and we'll see the answer that you get. So 0 squared is just 0, and then we have Vi squared minus 15.68. You can check the answer with me, and then it's just a matter of taking this to the other side and putting it in a square root. So if we take this, it's going to become 15.68, which is equals to Vi squared. And then to remove this, let me just wipe these equations. And to remove the square root, as we've always done, to remove the square, not the square root, you simply introduce a square root on both sides. And then Vi is going to be plus or minus, because it's in a square root, about 3.96 meters per second squared. So now it's a matter of, because only one of the answers can be true, it can either be negative 3.96 squared or negative or positive 3.9 meters per second squared. So we say that we know that this was moving up. If it's moving up, we said up is positive. So meaning Vi would actually be 3.96 meters per second. What is it? Upwards. So that is your answer. So now let us try to answer the second question. So now the second question wants us to calculate the change in time, the time it took for this ball to move from its initial position to the final position. And if you see, we have most of everything. We have the change in y, Vf, g, as well as Vi. Because we just calculated, what is it that we just calculated? Because we just calculated the initial velocity. So we also come back to our equations of motion and we say, okay, so we want, so most everything is there. For you can either use this equation to find a change in t, or this one to find a change in t, or even this one. So I'll pick the easiest one. You can use this one if you want to. And we say, okay, let us use Vf equals to Vi plus g, a change in t. Vf is 0. Vi, we said it is 3.96 plus a negative of 9.8, and then a change in t. And then how much is that going to be? So now it's just a matter of taking this to the other side. It becomes negative 3.96, and then we are left with negative 9.8, a change in t. To be left on the side with a change in t, we simply divide by 9.8, which is negative, and then you find your change in t to be a value of about 0.40 seconds. So you should at least come to that answer. This means that this ball took about 0.4 seconds to reach that maximum height. And this brings us to the end of this lesson.